Example 1 of the Solving Linear System with Matrices lab. We have the following system. We have 3x minus 3y minus 2z is equal to negative 1, 3x plus 5y minus 5z is equal to negative 6, and 3x plus 3y plus 2z is equal to negative 3. We want to solve this using a matrix. So what we need to do first, before we plug it into our calculator, is we need to write the augmented matrix. What that is when we take each of these x's, y's, and z's and the right-hand side and put them into a matrix as so, where the first row will be all of our x's, all of the coefficients of them, the second one will be all our y's, third will be all our z's, and the last one will be our equal sign, so what's on this side. And oftentimes they write a little dash there to indicate that this is the right-hand side. So the coefficient for the first one here is 3. The next one is 3. The last one is also 3. For our y's, we have negative 3 in front of the first one. We have a 5 in front of the second one, and a 3 in front of the last one. For our z's, we have a negative 2 coefficient, negative 5, and a 2. And for our equal signs, we have a negative 1 on the right side, a negative 6, and a negative 3. These have to all be in order in terms of what they are multiplied by. So this is all the x columns, the y columns, and the z columns, and the right-hand side columns. If these are not in order beforehand, you need to order them. So what we need to do next is we need to get our calculator. And we're going to input the matrix that we just found. So I'm going to press on. And we're going to go to matrix, which is the second button, and our x to the negative 1 button. We see all of our names of our matrices. We go to edit, and then we choose either one of our matrices that we want to edit, and we press enter. You can change the dimensions of the matrix as such by row versus column. This is a 3 times 4 matrix. And then edit the numbers that we have just already solved from this matrix right here and input it into this calculator. When you're done, you'll press second mode so that you can quit and go to the first page. Next, we want to simplify this matrix using RREF. To do so, we'll go back to matrix, so second, x to the negative 1. You see this menu again. We go to math. We scroll down to RREF, which is B. We press enter. And then we need to input a matrix. So we'll go back to our matrix area, and we go second, x to the negative 1. And under names, the names column, we choose the matrix that we just edited. I edited A, so I press enter. So you have RREF A, we press enter again, and it has found our augmented matrix for us. However, it's in decimals, so I want to make that into fractions. So what I'm going to do is I'm going to press math, this button right here, and I'm going to go to fraction. It's already on fraction 1. I'm going to press enter, and it says answer fraction. I press enter again, and it provides us with the last answer in fraction form. So we now have the simplified matrix, and this provides us with our answer. So I'm going to write that out. So we have for x, y, z, and equal column, our calculator has given us a 1, 0, 0, negative 2/3, a 0, 1, 0, negative 13 over 25, and for the last one it has given us a 0, 0, 1, and a 7 over 25. What this means is that if you put this back into equation format, it means that we have x for this first row is equal to, is 1x plus 0y plus 0z is equal to negative 2/3. In other words, x is just equal to negative 2/3. And then for this second row, we have 0x plus 1y plus 0z is equal to negative 13 25ths, which is essentially the same thing as saying y is equal to negative 13 over 25. And for this last row, we have 0x plus 0y plus 1z is equal to 7/25, which is the same thing as saying that z is equal to 7/25. So we have found our answer for this problem for our system. We can write it in ordered form place where we have our x, y, and z as such. So I will write it in that format. So we have a negative 2/3, negative 13/25, and 7/25. So we have a solution. Because we have a solution and this is a linear system, we can go back to our following table and know that because our two lines intersect exactly once at the ordered pair that we found, the system is consistent. So our system is consistent and we have found an answer.